so far I was talking about a kind of discrete measurement. I fire one particle at you, and looking at where it bounces off, I can either learn what the momentum exchange was or the position. If I don't want to disturb you very much, I use a particle that's not going to have a very big momentum change. And what we discover is I can't have very good resolution. I'm not going to get a lot of information about where you are. Then again, whenever real-world experimentalists do measurements, they know it's hard to get a lot of information from any one measurement. That's why we take measurement for hours or years if we're CERN or something like that, and we average and build up statistics. It's not that we learned about the existence of the Higgs boson from one muon that landed in one detector somewhere. We needed to do the statistics. So in the 1980s, Aharonov and his collaborators started thinking about this and realized I can do a measurement that doesn't disturb the system very much. And if I do it millions of times and I look at the average, I still learn on average what the system was doing. I don't learn on one particular trial exactly where it was, but maybe that's not what I'm interested in. So the reason this gets people like me excited is because there's a strange issue in quantum mechanics where we're often told not to think too much about the past, not to think about the history of a system or how to get where it is. In fact, we're told unless you actually built your experiment to measure X at the end of the day, you shouldn't even talk about X. Only talk about the things that you've built your apparatus to measure. And those of us who are realists want to say, well, I'd like to say something about what X was before I measured it, or what P was before I measured it. I mean, to me, the simplest case is the following. Fire a particle from this position, detect it over here at this position, and ask how fast was it moving, or what angle was it moving at? Classically, I'd say, well, obviously it must have been moving along that line, right? Quantum mechanically, that's not so clear. And yet, we ask ourselves, is there some way I could talk about what the average momentum of the particle had been after I emitted it, but before I detected it? And the problem is, you need to condition on this detection event. You have to say, I don't just want to look at the whole wave function, and the whole wave function is spreading out all over the place, and its average momentum is 0. I want to know just about the part of the wave function that reached this detector. How do you even begin to calculate that? And the reason that, let's say, from the 1960s to the 1980s, this seemed like an intractable problem was that if I did measure the momentum along the way, I would disturb the particle. We've just been talking about how measurements disturb particles. And then if I happened to find the particle at my detector, I'd say, well, it's not that was the path the particle was taking to the detector. It's just that you kicked the particle when you made this measurement, and that's what sent it to the detector. So this is why starting in 1988, when Aharonov, Albert, and Weidmann realized that you could make the measurements weekly, they were able to say, wait a second, if we kept measuring this average momentum or whatever we wanted to know, but without disturbing the particle, then sometimes the particle would reach this final detector. And on those occasions, I could go back and look at my measurement result and say, on average, whenever the particle made it there, this is what my meter read. So this was the average momentum, not of all the particles, but of the particles that made it from point A to point B.
When I'm deep in research, reading papers on, say, the philosophy of mind or quantum gravity, it may seem sterile, but I still don't want my ISP logging every single page that I visit. ExpressVPN prevents exactly that. Your internet service provider, your ISP, can see, they can log, and they can, in the US, legally sell a record of everything you do online. ExpressVPN encrypts all your traffic and reroutes it through secure servers so your browsing history stays entirely yours. I travel for interviews and conferences constantly, and connecting to hotel airport Wi-Fi without protection is something I'd often kick myself for afterward. ExpressVPN's encryption makes those public networks safe. It can be used to totally unlock geo-restricted lectures and content by changing online location to any of 105 countries. There's no compromise on speed either. It's consistently among the fastest VPNs out there. The fragility of hunting for workarounds just vanishes. Find out how you can get up to 4 extra months by clicking the link in the description box below, expressvpn.com/theoriesoferythingyt. That's expressvpn.com/theoriesoferythingyt.
So I wish I hadn't named these things weak measurements. To me, what's interesting about it is they're conditional measurements. It made it possible quantum mechanically to say, what is the average momentum of the particles that later on are guaranteed to get to this point? If I find the particle here, what was it doing before it got there? And that's something that a lot of traditional textbook quantum mechanics had denied being even possible. So in this quest to understand what is quantum mechanics really telling us about the nature of the world, about external reality, it seemed really important to me to be able to correlate final events with these measurements. And that's what weak measurement allows.
Is there something more to weak measurements than simply measuring a system's weekly over and over in order to get some picture, but just many hazy pictures, but then you average out these pictures? Because it seems like that wouldn't take until the 80s then. It seems like 5 years after Heisenberg already put that idea in our minds, we would have thought, well, why don't we just disturb it less and less, but take many snapshots or many.
Yeah, it's a great question. I don't know of earlier work on it, but of course, everything these guys did is building on the 1926 theory of quantum mechanics, and there's no good reason that someone in the 1930s could not have done this, except it's not what they were looking for. It's not what they were motivated to do. We've all been trained with the idea of a measurement as this kind of mathematical operation where you get a precise result. And of course, everyone knew early on, no measurement is absolutely precise. But the normal approach of physicists is to say, well, that's just experimental reality. We'll deal with that later. We'll add the uncertainties later and say, okay, we can't do the perfect job, but this is, the gold standard that we're aiming at. And it was really new to say, no, we actually want the uncertainty. I think there was also a conceptual shift. Another of Aharonov's big interests has been in the time symmetry of quantum mechanics. So like classical physics, all of quantum mechanics, leaving aside weak interactions, which isn't really fundamental to quantum mechanics, is time reversal invariant, meaning it is just as easy or difficult to predict the future from my present observations as to retrodict the past. And there's no mathematical difference between the two. Except we're also taught in quantum mechanics that there's measurement, and that measurement is this mystical event that we never define really clearly, but that breaks the time symmetry, because after a measurement, the state is completely reset. There's no experimental evidence whatsoever that we need to think of that as breaking time reversal symmetry. There's no reason when I find a particle at some position that I have to use that new state to calculate the future wave function, but something different to calculate the past. And yet that's what we were all taught. And Curt has been struggling for decades with the question of how to make sense of the symmetry of quantum mechanics. So he really wanted to say, if I know what a system was doing at t = 0, and I know what a system is doing at t = 1, both of those pieces of information should be equally useful to tell me what was going on at t = 0.5. And it's weak measurement that allowed him to mathematically show that that was true.
So to Curt, I spoke to him on the podcast. I think I have the first podcast with him ever.
Really?
Maybe the only one. I don't know why he said yes to me. Maybe I got him on a good day.
Special.
And so he told me that implies to him that the future informs the past. Ontologically, metaphysically.
Yeah.
Whatever that means.
Yeah, I find that difficult. Curt is much smarter than I am, so I don't want to say he's wrong. But I will say that to my mind is the religious side of his belief. As I said, we separate out the formalism that we can prove from what we argue about what it teaches us about reality. And the second is kind of a little more subjective at first and, harder to make rigorous. So I find it really interesting that that's the conclusion he leaps to from his equations.
As far as you know, am I mischaracterizing him, or have you also heard this from him?
No, I think that's reasonable. And there are, as I said, many people who are very, very seriously thinking about this idea of retrocausality, that the past affects the present. I don't know what the arrow of time is. That's one of the deepest mysteries in physics. It, in some sense, predates quantum mechanics. It becomes maybe more dramatic with quantum mechanics. I think it's something fascinating to think about. So,
Oh, sorry. I was like a professor. I was like a student in the classroom. Sir, I was going to say...
much more polite than the students, but aren't you?
I was going to say then, just connecting back to our earlier part, do you then imagine that there are several arrows of time, that time sub 1, time sub 2, and that some could go forward, some can go backward?
I certainly think that's possible in a laboratory scale setting. I think for the universe, as far as we can tell, there's one arrow of time, but there are different ways to define it. As you say, we have working definitions to grope towards something. So, there's the second law of thermodynamics when saying which direction does entropy increase. And okay, it increases in the same direction as you and I know time evolves. Is that a coincidence, or can you prove that once you have the second law, the psychological arrow of time must follow from it? I'm tempted to say the latter, but I've had trouble actually showing rigorously how that would occur. We don't currently believe that the universe is supposed to stop expanding and collapse on itself, but we can imagine universes that were going to do that. And there were speculations that when the universe turned around, that cosmological arrow of time reversing would also reverse the entropy and psychological arrows. So you could imagine saying, oh, it'll look really weird when the universe turns around and people all realize they're heading towards the big crunch. And someone else saying they're never going to realize that because for them, time will be running backwards too. So we all think the universe is expanding. And there's a law of physics that shows that what feels future to you is always the expanding universe. We don't know that that's true. And we don't think it's the real universe anyway. What I do think is interesting is that even classically, to understand the origin of the thermodynamic arrow of time seems to require putting it in by hand. And people gloss over that when they teach thermodynamics, but it's the best of our current understanding, I would say, that all we can do is say the reason time is moving in one direction now is because we live in a universe that happened to start in this particular way. And if it hadn't started that particular way, maybe we wouldn't have that arrow of time. But we can, go back and simplify the explanation. And that's what physics usually does, right? We show you can explain this effect by postulating one axiom, but I can't tell you where the axiom came from. I can't tell you why the Big Bang happened. But if we just assume that one thing, the rest follows. There are people who argue quite reasonably, maybe the universe isn't set just by one particular past boundary condition 15 billion years ago or whatever it is, but by some other boundary condition in the future. Why is that any less likely? And if our universe is conditioned both by how it has to start by some law of physics I don't know yet, and how it has to end by some other law I don't know, then that does guarantee a lot of things about the middle. And in that sense, that future condition would be constraining what we're doing right now. That's really not crazy, but I don't know where it would come from.
With Heisenberg's uncertainty, we talked about momentum and position, but there's obviously the conjugate side of other variables. And you've talked about negative time. So is there anything about one of those 4 other times or 8 other times or what have you that could potentially be negative that would allow you to borrow energy? I mean, sorry, not borrow energy, but violate the Heisenberg uncertainty in some other manner?
I'm not sure what it means to borrow something to violate the uncertainty principle there. I mean, honestly, I was giving you this picture of how you can think of photons traveling through atoms by temporarily giving their energy to the atom and taking it back. When you're very far off resonance, like light going through a piece of glass that's essentially completely transparent, people do often describe that through the uncertainty principle, saying that, well, you can't violate energy conservation permanently, but you can temporarily borrow a little energy for time less than h bar over delta E. And that actually gives you a pretty good understanding of the time scale for propagation far from resonance, not on resonance. I don't see how any of these uncertainty principles can help you, though, with the negative time.
What's a misconception that many graduate students have when they come to you, or physics students I'm talking about physics, that you have to dispel constantly? I'm not talking about undergrads. undergrads have various ideas, and high school students, of course. I mean, what's something that is taught that you say that's not taught correctly, and when it comes to me, I have to reteach it?
I mean, there are a lot of there are a lot of technical things that one wants to go over more carefully, depending on what field one's in. I'd say the bigger issue just has to do with the role of experiment, how to think about the interplay between theory and experiment. I don't like the way that we teach students about experimental physics. They come out with a very strange mechanistic view of what it means to write a lab report and report what you were supposed to have seen. It's probably not specific to experiment. It's true in theory as well, because we teach people the stuff that we already understand really well. And it's natural to come out thinking my whole job is to just reproduce the right answer. And of course, once you're doing research, you don't know the right answer. And the important thing is to be skeptical of yourself and, limit what your conclusions are and talk about the range of uncertainty. I'd say that's the harder thing. But these issues about measurement are probably a good one as well. This idea that the ideal measurement is collapse. And whenever we have an uncertain measurement, it's just because our experiment isn't good enough. I think these days we try to pull people beyond that and teach them instead that what the theory should do is model what measurements actually are in the real world. And every real measurement has some finite uncertainty. And there's a better formalism that isn't taught in undergraduate quantum mechanics that's much more general and deals with that properly.